There is an iron atom moving through your body right now. It is inside a red blood cell, which is inside a vessel so narrow the cell has to fold itself to pass through. The atom itself is not large enough to see, not large enough to feel, not large enough to be aware of. It has been doing this moving, carrying oxygen, cycling for as long as that particular cell has existed, and before that, it was somewhere else entirely, not in a body, not on Earth, not in this solar system. The iron in your blood was made in a dying star, not a star that died near here, and not recently. The event that forged that atom took place billions of years before the Earth existed, in a stellar core that spent millions of years building toward a single catastrophic moment. The iron is a relic of that moment, but iron is not the oldest thing in you. The hydrogen in your body, the hydrogen that makes up more than 2/3 of your atoms, is older than any star that has ever existed. It formed in the first few minutes after the Big Bang, nearly 14 billion years ago. It has been drifting through the universe ever since, and the gold in you trace amounts, real and measurable, came from somewhere else again. The collision of two dead stars, an event so rare and so violent that we did not directly observe one until the year 2017. Your body is not one thing from one place. It is an assembly of separate events, spread across billions of years and across the most extreme environments the universe has ever produced. Hello, and welcome to Sidereal. Tonight we are going to follow that assembly backward element by element, event by event, and find out where the atoms in your body actually came from. If this kind of slow, long exploration is useful to you for sleep or winding down, a like or a subscribe genuinely helps the channel reach people who'd find it. And I am always curious where you are listening from. Drop your location and time in the comments. Before we begin, one question worth sitting with tonight. Every element in your body has a different age and a different birthplace. So how did anyone ever work that out? The periodic table does not come with a postmark. By the end of tonight, you will be able to point to different parts of your own body and name the event, the specific cosmic event that made them. Let us begin. The average adult body contains roughly 7 octillion atoms. That number 7, followed by 27 zeros, is larger than the number of stars in the observable universe. It is large enough that writing it out in standard form means nothing to the mind. What it means, in practice, is that you are an object built almost entirely from things too small to detect individually, assembled into something that breathes and thinks and lies in the dark, listening to a voice talk about where it came from. Of those 7 octillion atoms, more than 2/3 are hydrogen, the lightest, simplest element, 1 proton, nothing else. By count, hydrogen dominates everything. By mass, the picture shifts. Because hydrogen is so light, oxygen makes up about 65% of your body's mass, carbon around 18%, hydrogen roughly 10%, nitrogen about 3%, calcium, phosphorus, and a handful of other elements make up nearly all the rest. 6 elements account for approximately 99% of what you are. That is the composition. But composition is not the same as origin. To know where you came from, you have to ask a different question, not what you were made of, but where each of those things was made. And the answer is not a single place, and not a single era. Different elements in your body arrived from different events separated by billions of years. The oldest is hydrogen, and to understand the hydrogen in you, you have to go back to a time before any star had yet ignited. In the first fraction of a second after the Big Bang, the universe was too hot for nuclei to exist. The temperatures were so extreme, many billions of degrees Celsius, that any proton and neutron that touched were immediately blasted apart by the surrounding radiation. The universe was a plasma of elementary particles, quarks assembling into protons and neutrons, immediately colliding, immediately separating. Then the universe expanded. As it expanded, it cooled. And as it cooled, something became possible that had been impossible for the entire first second of time. Nuclei could form and stay formed. This window opened at roughly 1 second after the Big Bang, and it closed at roughly 3 minutes. In those 3 minutes less time than it takes to boil water, the universe ran through an episode of nuclear fusion that set the composition of all the ordinary matter that would ever exist. Protons and neutrons combined into deuterium, Deuterium peaked in abundance at around 100 seconds, then was swept up into helium. Helium accumulated until it represented roughly 24 to 25% of all ordinary matter by mass. A trace of light helium formed, a trace of lithium formed, and then it stopped. The reason it stopped is not that the universe ran out of material, it is that the universe ran out of time. As the temperature dropped below the threshold for nuclear reactions, the fusion window closed permanently. What remained when it closed was the complete inventory of Big Bang nucleosynthesis, roughly 75% hydrogen by mass, 24 to 25% helium, and traces of 2 or 3 lighter isotopes too small to concern us here. Everything else, every atom heavier than lithium, is missing from this list. Carbon is missing. Oxygen is missing. Iron is missing. Gold does not exist yet anywhere in the universe. There is a technical reason the window closed before it could build heavier nuclei, and it is worth understanding because it shaped everything that came after. There is no stable nucleus of mass 5 and no stable nucleus of mass 8. This sounds like a minor bookkeeping detail. It is not. It means that when a helium nucleus tries to absorb another particle to become something heavier, the product immediately disintegrates. There is no stepping stone. The chain breaks. The Big Bang could not climb past helium in the time available because the rungs of the ladder it needed did not exist. So the early universe produced the lightest elements and stopped. Everything that makes life possible, the carbon in your DNA, the oxygen in the air, the iron in your blood, had to come from somewhere else and from some other era. Here is what that means for the hydrogen in you specifically. That hydrogen in the water in your cells, in the proteins folded inside them, in every molecule in your body that contains a hydrogen atom, has been in the universe for nearly 14 billion years. It formed in those 3 minutes. It then spent billions of years as diffuse gas, drifting through the interstellar medium, before some of it was swept into the cloud that collapsed to form the solar system, before some of that found its way into the oceans, before some of that became part of you. The hydrogen in your body is roughly the same age as time itself. That claim is worth sitting with for a moment, because it is a physical fact with a specific implication. The hydrogen atoms that move through your body right now have been doing their hydrogen thing, unchanged, through the entire history of the universe. Stars formed and died around them. Galaxies assembled. Billions of years of cosmic history unfolded, and those hydrogen atoms just kept drifting. They were present before the first star turned on. They will be present long after the last one burns out. There is a refinement to that picture worth adding, because it makes the age of your hydrogen more precise rather than less. The nucleus of a hydrogen atom is a single proton, and protons had existed since the first fraction of a second, long before the 3-minute window. What the 3 minutes decided was not whether hydrogen would exist, but how much of it would survive uncombined. Roughly 3/4 of the protons were left over, unfused, when the window closed. Those leftover protons are the hydrogen nuclei in you, but a bare proton is not yet hydrogen in the way you would recognize it. For the first 380,000 years, the universe was still too hot for electrons to stay attached to nuclei. The cosmos was an opaque fog of charged particles and trapped light. Only when the temperature finally fell to a few thousand degrees did electrons settle onto the waiting protons, and hydrogen became a neutral atom for the first time. At that same moment, light was set free to travel in straight lines across the universe, and that light is still arriving now, stretched by the expansion of space into faint microwaves, detectable from every direction in the sky. We found that light by accident. In 1965, 2 physicists at Bell Laboratories in New Jersey, Arno Penzias and Robert Wilson, were trying to use a large horn-shaped antenna for radio astronomy and could not get rid of a persistent background hiss. The hiss came from every direction, day and night, in every season. They checked the equipment, they suspected the pigeons nesting in the antenna, and cleaned out the droppings. The hiss remained. What they were hearing, it turned out, was the cooled afterglow of the early universe, the light released when hydrogen first became an atom, predicted by the Big Bang account and detected by 2 people who were not looking for it as a noise they could not switch off. It is the oldest light there is, and it confirmed, more than anything else, that the universe had a hot, dense beginning of exactly the kind that produced your hydrogen. So the hydrogen in your cells has two birthdays. The proton at its core dates to the first second. The atom, proton, and electron together dates to 380,000 years later, the same event whose afterglow still fills the sky tonight. Either way, it is older than every star. Now, the other side of the inventory. If hydrogen is in the list, and carbon, oxygen, and iron are not, then those elements had to be built somewhere, at some point, after the Big Bang. The question of where, which is the question that takes up the rest of tonight, was not answered quickly. It took most of the 20th century, a sequence of discoveries that each overturned what everyone had assumed was obviously true, and at least one scientist being told that her correct conclusion was clearly impossible. The first step in that sequence was figuring out what stars are actually made of. This sounds like it should have been settled early. It was not. Before 1925, the dominant assumption in astrophysics was that stars were, in their elemental composition, something like hot versions of the Earth, predominantly iron, silicon, calcium, and the other heavy metals that made up the rocks underfoot. Stars emitted light that could be analyzed through spectroscopy, and those spectra contained lines corresponding to many of those same elements, so the assumption seemed reasonable. It was wrong by a factor of roughly 1,000,000. The person who discovered this was 24 years old at the time, working on her doctoral thesis at what was then Radcliffe College at Harvard, and the discovery was immediately dismissed by the most powerful astronomer in America. Her name was Cecilia Payne, and the method she used was entirely new, applying an equation derived by the Indian physicist Meghnad Saha to connect the pattern of spectral lines in starlight to the temperatures and abundances of the elements producing them. What her analysis showed was that the most abundant element in stars by an enormous margin was hydrogen, not iron, not calcium, hydrogen followed by helium, followed by a comparatively tiny amount of everything else. Hydrogen appeared to be roughly 1,000,000 times more abundant in stellar atmospheres than the heavy metals the field had assumed were dominant. When she wrote this up in her thesis titled Stellar Atmospheres, she included the result clearly. The calculation was there, the evidence was there. And then, in the final version of the thesis, she added a sentence that has stayed with historians of science ever since. The enormous abundance she had derived for hydrogen and helium, she wrote, was almost certainly not real. She did not believe that sentence. She had been pressured to write it by Henry Norris Russell, the Princeton astronomer who served as external advisor to the Harvard Observatory and who, in practice, was the dominant voice in American stellar physics at the time. Russell had co-created the diagram of stellar classification that every astronomy student still learns. He read her thesis draft and wrote back to her that the high hydrogen abundance was, in his view, clearly impossible. He was on her thesis committee. Without his endorsement, the thesis would not be accepted. She had spent years on this work, and so she inserted the disavowal while leaving every single calculation intact, so that anyone who wanted to could check her work and see what the numbers actually said. 4 years later, in 1929, Russell published his own derivation of the abundance of elements in stars using a different method. He found the same result, overwhelming hydrogen. He cited her work and noted that his numbers agreed with hers. He did not mention that he had originally told her that her numbers were impossible. For years afterward, the discovery was widely attributed to Russell. Payne continued working at Harvard, producing an extraordinary body of work on variable stars and stellar luminosity, with none of the formal recognition a man of equivalent output would have received. She became Harvard's first female full professor and department chair in 1956. In 1976, she received the Henry Norris Russell Lectureship, the prize named for the man who had told her she was wrong. She reflected on it in her memoir. She wrote that she had been to blame for not having pressed her point, that she had given in to authority when she believed she was right. Decades later, when the importance of the work was beyond dispute, a leading astronomer of the following generation looked back and judged her doctoral thesis the most brilliant ever written in the subject. At the time of writing, it was a result she had been required to call almost certainly not real in her own pages, at the insistence of the man who would confirm it 4 years afterward. The discovery itself, regardless of who received credit for it, changed what stars were. They were not hot rocks. They were vast reservoirs of hydrogen, the most abundant element in the universe. the element produced in the first 3 minutes, burning, fusing, building. This opens a question that the rest of tonight will work through. If stars are mostly hydrogen and helium, what are they actually doing with it? How do they shine? And more importantly for the material in your body, how does a star made of hydrogen end up producing the carbon and oxygen and iron that would eventually find their way into you? The question Cecilia Payne had answered was not a small one. It was not a refinement of existing knowledge or a correction to a minor calculation somewhere in the literature. She had shown that stars, all stars, consistently, everywhere she looked were made overwhelmingly of hydrogen and helium, not of the heavy elements the field had assumed for decades, and she had been pressured into disowning the result in the same document that proved it. What she had not answered, and what nobody in 1925 could answer, was the question that followed immediately from her discovery. If stars are made of hydrogen, what are they doing with it? Stars burn. They have been burning for billions of years. Something is fueling them. And given that their fuel is hydrogen, the lightest element in the universe, the element forged in the Big Bang's first 3 minutes, whatever is happening inside them, is not combustion in any ordinary sense. A star burning hydrogen like a coal fire would exhaust itself in a few thousand years. The sun is 4.5 billion years old. The arithmetic does not work. The general shape of the answer had been guessed years before anyone could prove it. In 1920, the English astronomer Arthur Eddington had argued that the sun must run on subatomic energy, that hydrogen was being converted into helium deep in its core, and that the small amount of mass lost in the conversion was being released as the sun's light. He even suggested, with remarkable foresight, that this process might one day be understood well enough to control. His critics objected that the interior of the sun was not hot enough for the nuclei to overcome their mutual repulsion and fuse. Eddington's reply has survived as one of the sharper lines in the history of physics. He told them, in effect, to go and find a hotter place. He was confident the sun was the furnace. He simply could not yet say how the furnace worked. The answer was nuclear fusion, but knowing that fusion must be the answer, in a general sense, was not the same as knowing which specific reactions were responsible, or in what sequence, or how the numbers balanced. Those questions took another decade and a half to work out. When they were finally answered, the work was done in a sequence of events that began with a physicist being repeatedly urged to attend a conference he had no particular interest in attending. Hans Bethe was 32 years old in 1938, a German-born physicist who had moved to Cornell University after the Nazis came to power, and who by that point had already made substantial contributions to nuclear and atomic physics. He was not, at that moment, especially focused on stellar energy. Edward Teller, who was organizing a conference in Washington on the problem of energy generation in stars, had to press him repeatedly before he agreed to come. What Bethe heard at that conference, and what he worked through in the weeks that followed, produced a paper published in 1939 in the Physical Review under the title Energy Production in Stars. That paper founded the field of nuclear astrophysics. It was the first precise, quantitative account of what a star is actually doing at its core. Bethe showed that there were two distinct processes by which a star could convert hydrogen into helium, depending on the star's mass and temperature. In stars like the Sun, the dominant mechanism is called the proton-proton chain. Two protons, two hydrogen nuclei collide and fuse to form a nucleus of deuterium, releasing a positron and a neutrino in the process. The deuterium then captures another proton to become light helium. Two light helium nuclei then collide and produce ordinary helium, releasing two protons back into the plasma. The net result of this sequence: 4 protons go in, 1 helium nucleus comes out, and a small amount of mass is converted into energy, according to the relationship Einstein had described 34 years earlier. That conversion is what powers the sun, not combustion, not chemical energy. The difference in mass between 4 protons and 1 helium nucleus, a difference small enough to seem negligible, is released as energy every time the reaction completes. The sun completes it so many times per second that the numbers become difficult to hold. Roughly 600 million tons of hydrogen are converted to helium in the sun's core every second. The mass deficit from those reactions, translated into energy, is what arrives at Earth as sunlight. In more massive, hotter stars, a second process dominates. Bethe worked this out as well, building on earlier work by the German physicist Carl von Weizsäcker. This is the carbon-nitrogen-oxygen cycle, in which carbon acts as a catalyst. A carbon nucleus absorbs a proton and becomes a nucleus of nitrogen, which decays. The chain continues through several steps, absorbing protons along the way, until the original carbon is regenerated and a helium nucleus is released. The carbon is not consumed. It enables the reaction and comes out intact at the other end. In the most massive stars, this cycle is the primary engine. The Sun uses a small amount of the carbon-nitrogen-oxygen cycle. Roughly 1% of its total energy comes from that pathway. Stars more than about 1 1/3 times the mass of the Sun increasingly rely on it. Stars several times the Sun's mass are powered almost entirely by it. Bethe received the Nobel Prize in Physics for this work in 1967. The citation described his discovery of the reactions that supply energy in stars. The field of nuclear astrophysics, the study of how nuclear processes in stellar interiors produce the elements, the light, and the conditions that make the rest of the universe possible, traces its formal beginning to that 1939 paper. But hydrogen fusing to helium does not produce carbon. It does not produce oxygen. It does not produce iron. What Bethe had explained was the power source. It said nothing about the heavier elements. A star running on the proton-proton chain or the carbon-nitrogen-oxygen cycle is converting hydrogen to helium for billions of years, and at the end of that process, it has a core of helium and nothing beyond it. To get from helium to the carbon in your DNA, or the oxygen filling your lungs right now, the story has to take another step. And that step was much harder to work out, because it requires something that should not, by any straightforward physical reasoning, be possible at all. The problem is this: when two helium nuclei collide, they produce a nucleus of beryllium, specifically, the form of beryllium with 8 particles in its nucleus. That nucleus is extraordinarily unstable. It exists for less than 1/10 of a millionth of a billionth of a second before it decays back into 2 helium nuclei. There is no way to use it as a stepping stone to anything heavier in any practical sense, because it does not last long enough for anything to happen to it. And yet carbon exists. You are made largely of carbon. Every living thing is made largely of carbon. Carbon is the 4th most abundant element in the universe by mass. Something made it in enormous quantities and is still making it now inside stars. But the most obvious path to making it helium plus that unstable beryllium is blocked by the instability of the beryllium at every moment. The physicist who understood how to resolve this was Fred Hoyle, a Yorkshire-born astronomer whose relationship with the scientific establishment was, to put it generously, complicated. Hoyle had been arguing since 1946 that stars were the site of heavy element production, a position that put him at odds with George Gamow and others who maintained that the Big Bang had produced essentially all the elements, not just the lightest ones. He was developing the theoretical framework for stellar nucleosynthesis years before the experiments existed to test any of it. By the early 1950s, Hoyle understood the problem of the beryllium bottleneck clearly enough to see what the solution had to be. If carbon exists in the universe in the quantities it does, and it does, undeniably, then there must be a way for 3 helium nuclei to combine to form carbon. This is called the triple alpha process, because helium nuclei are also known as alpha particles. The sequence would be 2 alpha particles briefly form the unstable beryllium, and before the beryllium decays, a 3rd alpha particle is absorbed, producing carbon. But for this to work fast enough to produce the carbon we observe, the reaction needed to be dramatically enhanced by a resonance, an excited energy state of the carbon nucleus that would act as a kind of target, vastly increasing the probability that the 3rd alpha particle would be absorbed before the beryllium fell apart. Without a resonance, the triple alpha process would be far too slow. With one at the right energy, it could work. No such resonance in carbon had been detected. In 1953, Hoyle came to the California Institute of Technology, where William Fowler ran an experimental nuclear physics laboratory. Fowler was an Ohio-born physicist who had spent years measuring the nuclear reaction rates relevant to stellar interiors. Hoyle persuaded him to search for a specific excited state of carbon at an energy of approximately 7.65 million electron volts above the ground state. Not 7 million, not 8 million, approximately 7.65. Hoyle had derived the number from the requirement that carbon must exist in the observed quantities. The experiment was done. The resonance was found within a small margin of the predicted value. The reasoning behind that prediction is worth pausing on, because it ran in an unusual direction. Hoyle had not derived the carbon resonance from first principles, measuring nuclear properties and calculating upward. He had gone the opposite way. Carbon exists. Therefore, the physics that allows carbon to exist must be real. Therefore, there is an excited state of the carbon nucleus at approximately this energy, so go and look for it. The universe, in a sense, was the evidence. What we observe above us told us what must be true about nuclear physics below the level of direct measurement. There is a version of this story that has become somewhat inflated in popular accounts, the claim that Hoyle was using something like the anthropic principle, reasoning from the fact of human existence back to the nuclear physics required for it. The historian of science Helga Krag has argued carefully that this framing is a later invention, that Hoyle and his contemporaries at the time did not see the carbon resonance in those terms. The anthropic frame was applied in retrospect, beginning in the 1980s. The actual reasoning in 1953 was more straightforward. We observe carbon. The physics must permit its production. Find the mechanism. Either way, the resonance exists. The carbon nucleus has an excited state at 7.65 million electron volts. The triple alpha process works. Every carbon atom in the universe passed through that resonance at some point in the interior of a star. And there is a further complication that the story does not always include. Once carbon has been produced, it is in danger of being immediately converted into oxygen. A carbon nucleus can absorb another alpha particle and become oxygen. If this reaction were just slightly more efficient than it is, nearly all the carbon produced by the triple alpha process would be converted to oxygen, and the universe would have very little carbon. If it was slightly less efficient, nearly all the oxygen would remain as carbon, and the universe would have very little oxygen. As it happens, the rates of these two reactions, the triple alpha process producing carbon and the subsequent alpha capture converting carbon to oxygen, are balanced in such a way that substantial quantities of both are produced in stellar interiors. The carbon in your body and the oxygen you breathe are both products of this balance, held between two reaction rates that could, in principle, have gone differently. It is worth lingering on oxygen because it is not a minor character in this story. By mass, it is the most abundant element in your body, about 65% of you, more than everything else combined, and the third most abundant element in the universe, after hydrogen and helium. It is also made in greater quantity than carbon. As a massive star ages, it develops a layered structure, like the rings of an onion. Hydrogen burning in the outermost shell, then helium beneath that, then carbon, then neon, then oxygen, then silicon, each layer hotter and denser than the one wrapped around it, each fusing toward the center. Oxygen accumulates in those inner shells in enormous amounts and is poured into space when the star explodes. A core collapse supernova is, among other things, an oxygen factory. The oxygen you are breathing right now, in and out the oxygen that the iron in your blood exists to carry, was made in the interior of a massive star and released by that star's death. What Hoyle's work, and the long paper that followed it in 1957, had established was something Cecilia Payne's discovery had made possible, but had not, by itself, shown. Yes, stars are made of hydrogen, and inside those hydrogen-dominated stars, in cores that reach temperatures of tens of millions of degrees, fusion is climbing a ladder. Hydrogen to helium, helium to carbon, and oxygen. The furnace is building, but the furnace has a wall. It is not a wall that announces itself. You would not see it coming if you were watching from outside. A massive star burns hydrogen to helium for millions of years. When the hydrogen in the core is exhausted, the core contracts, heats up further, and ignites helium fusion, the triple alpha process, while hydrogen continues burning in a shell around it. When the helium is exhausted, the core contracts again, and the next fuel ignites. Carbon, then oxygen, then neon, then silicon. Each stage runs faster than the one before, because the energy released per reaction decreases as you climb the ladder, and the star must burn through its remaining fuel more rapidly to maintain the pressure that holds it up against its own gravity. Silicon burning takes approximately a day in the core of the most massive stars. Less than a day. The whole sequence from hydrogen to silicon is millions of years of gradual burning, followed by a frantic sprint toward an end that arrives very quickly. This is worth holding against the lifetimes involved, because it is one of the things about stars that does not get easier the longer you think about it. How long a star lives depends almost entirely on its mass, and the relationship runs the opposite way to intuition. The most massive stars, with the most fuel, live the shortest lives a few million years, sometimes less because they burn so furiously to hold themselves up against their own enormous gravity. The Sun, an ordinary middleweight star, will live for roughly 10 billion years and is about halfway through. And the smallest, dimmest stars, the red dwarfs, burn so slowly and so frugally that they can last for trillions of years, far longer than the present age of the universe. No red dwarf has died of old age yet. None has had time. The universe is not old enough. What this means for your body is direct. The massive stars that made your oxygen and your calcium and much of your iron lived fast and died young, which is why they were able to do their work, scatter their elements, and have those elements gathered into the solar system all within the time available before the sun formed. A universe that made only long-lived stars would not yet have produced you. It would still be waiting. Picture the final day from the inside, if you can stand to. In the core of a massive star, a region not much larger than the Earth holds more mass than the sun, fusing silicon into iron at a temperature of billions of degrees, racing through in hours what the earlier stages took ages to do. There is no warning. The star's surface, vast and luminous, gives no sign of what is happening at the center. From the outside, it is simply a bright star in the sky. Inside, the furnace has reached the one fuel it cannot use. And at the end of silicon burning, what accumulates in the core is iron. Iron sits at what physicists call the peak of the binding energy curve. Binding energy is the energy required to pull a nucleus apart into its constituent protons and neutrons. The binding energy per nucleon per particle in the nucleus rises as you move up from hydrogen toward iron, and then it falls as you move beyond iron toward heavier elements. Iron is, in this specific sense, very nearly the most tightly bound nucleus in nature, at approximately 8.8 million electron volts per nucleon. A neighbor of iron, a particular form of nickel, edges it by a hair on the most careful measurement, but for the purposes of a star, iron is the practical summit. There is nowhere meaningfully higher to go by fusion. What this means for a star is absolute and final. Every fusion reaction the star has run up to this point, hydrogen to helium, helium to carbon and oxygen, carbon to neon and magnesium, and so on, has released energy because the products were more tightly bound than the reactants. Moving from less tightly bound to more tightly bound releases the difference as energy. That energy is what holds the star up. Iron cannot do this. To fuse iron into anything heavier requires energy to be put in, not taken out. Iron is already at the top of the binding energy mountain. A star that tries to generate energy by fusing iron would need to consume energy to do so, and a star is not a device that can sustain that. The moment an iron core accumulates, the star has run out of fuel, not in the sense that it has used up one type and can switch to another, but in the absolute sense that the thermodynamic engine has reached a state it cannot work from. In the most massive stars, the iron core grows until it reaches approximately 1.4 times the mass of the Sun, the Chandrasekhar mass, the limit at which the pressure of tightly packed electrons can no longer hold the core up. When the core exceeds that mass, it collapses. The collapse takes less than a second. The outer layers, suddenly unsupported, fall inward and then rebound in a shock wave. The star explodes. That limit has a name because of a young man on a boat. In 1930, a 19-year-old Indian physicist named Subramanian Chandrasekhar was making the long sea voyage from Madras to England to begin his studies at Cambridge, and during the passage he worked out a calculation about the fate of white dwarfs. Combining the new quantum physics with Einstein's relativity, he found that the pressure of crushed electrons could only hold up so much mass that above roughly 1.4 times the mass of the Sun, no white dwarf could support itself, and the matter would have to collapse into something far denser. It was a clean, fundamental result, and it implied that the most massive stars faced an end stranger than anyone had assumed. The most powerful astrophysicist of the age did not accept it. Arthur Eddington, the same Eddington who had been right about fusion, who had told the doubters to go and find a hotter place, rose at a meeting of the Royal Astronomical Society in 1935 and ridiculed the young man's result in front of the assembled field. He could not believe nature would permit a star to behave so absurdly. There ought, he said, to be a law to prevent it. Eddington's prestige was such that the field largely deferred to him, and Chandrasekhar, unwilling to spend his career fighting a giant, eventually turned away from stellar structure altogether and moved to the United States, where he worked on other problems for decades. He was right, and Eddington was wrong. There is no law to prevent it. Above the Chandrasekhar mass, the collapse happens, and that single limit governs both halves of the iron story. When a massive star's iron core crosses it, the core collapses, and the star explodes as a supernova. When a white dwarf in a binary is pushed across it, the white dwarf detonates. The number Chandrasekhar found on a boat at 19 is the threshold that decides when a star can no longer hold itself together. He received the Nobel Prize for it in 1983, 48 years after Eddington stood up to say it could not be true. This is one reason there is iron in your blood. Not because iron was easy to make, because iron was the wall. Every massive star that burned through its fuel and reached the iron core produced iron in the final frantic stage of its life, and then detonated and scattered that iron into the space around it. The iron eventually became part of interstellar clouds, which collapsed into new stars and their accompanying planetary systems, and some of it found its way into the oceans and the rocks and the organisms that evolved there. We know this not as a theoretical reconstruction, but as a direct observation. On the 23rd of February, 1987, light from an exploding star in the Large Magellanic Cloud reached Earth after a journey of approximately 166,000 years. The explosion catalogued as supernova 1987A was visible to the naked eye in the southern hemisphere. It was the first supernova close enough to study in detail with modern instruments, and it confirmed, in real time, things that had until that point been mathematical predictions about what happens at the end of a massive star's life. It was found, in the first instance, by eye. A young Canadian astronomer named Ian Shelton was working at an observatory in the mountains of northern Chile, and on the night of the 24th of February, he stepped outside and saw a star in the Large Magellanic Cloud that had not been there before, bright enough to see without a telescope. It was the brightest supernova visible from Earth since the one Johannes Kepler had recorded in 1604, nearly 4 centuries earlier. For a few weeks it hung in the southern sky, a new point of light marking a star that had, in fact, ceased to exist some 166,000 years before, when the light now arriving first set out. The star was already long dead. The news had simply taken that long to cross the distance. But the confirmation came in 2 messengers, and the more remarkable one arrived first. A few hours before the light reached Earth, 2 large underground detectors registered a burst of particles that had passed through the planet entirely, barely interacting with anything, neutrinos from the collapsing core. The Kamiokande detector, buried in a zinc mine in Japan, registered 12 of them. The Irvine, Michigan Brookhaven detector, in a salt mine beneath Lake Erie in Ohio, registered 8. 12 and 8 in detectors that occupy large volumes of water designed to catch the faintest possible signals, because the neutrinos that arrive from a collapsing stellar core number not in the dozens but in something closer to 10 to the power of 58, and almost all of them pass through the entire Earth without leaving a trace. Those 20 particles were enough to confirm the model. The light that followed told the rest. The supernova's brightness, tracked over the weeks and months after the initial flash, did not fade the way an ordinary explosion would. Instead, it followed a curve that matched, almost exactly, the known radioactive decay chains of freshly synthesized nickel and cobalt. The form of nickel produced in the explosion decays to a form of cobalt with a half-life of approximately 6 days. That cobalt then decays to iron with a half-life of approximately 77 days. The light curve of the supernova traced that 77-day half-life precisely. Gamma-ray lines from the decaying cobalt were detected by orbiting instruments directly in the months after the explosion. What this means, concretely, is that the light we were watching from that exploding star was powered by the radioactive decay of iron being made. The manufacture of iron, the same process that produced the iron now in your blood, was not inferred from theory or reconstructed from ancient geological record. It was observed, in real time. 166,000 years after the light left the explosion, instruments on and around Earth measured the gamma rays coming off a specific isotope of cobalt decaying into iron. At the rate that isotope decays, in the quantity that a stellar core of that size would produce, the star synthesized approximately 0.07 times the mass of the Sun in iron during the explosion, an enormous quantity, scattered into the surrounding space by the force of the shockwave, added to the interstellar medium, available to be swept into the next generation of stars and their planets. That is the iron wall, and what lies beyond it. But there is a complication in the iron story that the supernova does not tell you, and it matters for the iron in your blood specifically. Core collapse supernovae, the death of massive stars, the kind we watched in 1987, are not the only source of iron in the universe. They are not even the largest one. Most of the iron in the galaxy, by the best current accounting, came from a different kind of explosion entirely, the detonation of a white dwarf. A white dwarf is what a low-mass star leaves behind when it dies quietly, not in a supernova, but by shedding its outer layers and exposing the dense, inert core that remains. Our own sun will end this way, several billion years from now, a slowly cooling ember about the size of the Earth, holding roughly half a solar mass of carbon and oxygen in a sphere you could fit inside a planet. On its own, a white dwarf does nothing dramatic. It cools for billions of years. It is the long, undramatic afterlife of an ordinary star. But white dwarfs are often not on their own. Most stars form in pairs or groups, and a white dwarf with a companion star can pull material from that companion onto its own surface, or two white dwarfs in a binary can spiral together and merge. Either way, if the white dwarf's mass is pushed toward that same Chandrasekhar limit of approximately 1.4 times the mass of the Sun, something irreversible happens. The carbon in the core ignites, and because a white dwarf is held up not by ordinary pressure, but by the same tightly packed electrons that resist compression in a collapsing stellar core, it does not respond to the sudden heat by expanding and cooling the way an ordinary star would. The fusion runs away. Within seconds, the entire white dwarf is consumed in a thermonuclear explosion that leaves nothing behind. The star is not damaged. It is gone. This is a Type 1, a supernova, and it produces iron in abundance, roughly 0.6 times the mass of the Sun in freshly made iron per event, more than a single core collapse supernova typically yields. Because these explosions have been occurring throughout the history of the galaxy, and because each one is so productive, they are responsible for more than half of the iron in the universe today. It is worth holding the cumulative scale of this for a moment, because no single explosion made you. The iron and calcium and oxygen in your body are not the product of one star's death, but of the pooled output of an enormous number of them. Our galaxy produces a few supernovae of all kinds each century, and has been doing so for well over 12 billion years. Across that span, something on the order of hundreds of millions of stars have died in explosions and added their manufactured elements to the common reservoir of gas from which new stars and planets form. The cloud that became the solar system was enriched not by a single donor, but by that accumulated inheritance generation upon generation of stars living, dying, and seeding the next batch for billions of years before the Sun ignited. The atoms in your body are a sampling of that long pooling, drawn from countless separate deaths you can never identify, mixed together so thoroughly that the iron in one of your cells and the iron in another may have come from explosions billions of years and thousands of light years apart, which means that, statistically, much of the iron moving through your blood right now was not forged in the death of a massive star at all. It was forged in the obliteration of a white dwarf, the burned-out core of a star, not unlike the Sun, ignited by a companion, and destroyed completely in a few seconds. The iron in your hemoglobin has two possible biographies, and we cannot say which atom followed which. Some of it came from a star that collapsed. Some of it came from a star that detonated. Both kinds of explosion fed the same interstellar clouds, and both kinds of iron ended up, billions of years later, in the same body. Type 1, a supernovae, have a second importance worth naming because it loops back to the rest of cosmology. Because every one of these explosions involves a white dwarf reaching the same mass threshold before detonating, they release very nearly the same amount of light each time. That consistency makes them usable as distance markers, standard candles, in the language of astronomy. It was by measuring the brightness of these exploding white dwarfs across the universe in the late 1990s that two teams of astronomers discovered that the expansion of the universe is accelerating, driven by something we still call dark energy, because we cannot say what it is. The same explosions that made the iron in your blood are the ones that revealed we do not understand what most of the universe is doing. So the iron has two sources, and both are explosions, and one of them quietly rewrote what we thought we knew about the fate of the cosmos. But iron, however it was made, is the heaviest element that fusion can build. The wall is absolute. Every element in you that is heavier than iron, and there are several, including elements your body depends on to function, got here by an entirely different mechanism, one that has nothing to do with fusion and everything to do with what happens when stars run out of time. Every element heavier than iron arrived in the universe by a path that fusion cannot take. Iron is where the binding energy curve peaks and the furnace goes cold. Anything beyond it, copper, zinc, iodine, gold, uranium, required a different process entirely, one that does not release energy but instead consumes it, and one that requires conditions so extreme that for most of the 20th century, scientists could not agree on where in the universe those conditions existed. The mechanism is neutron capture. A nucleus that has already been built by fusion can absorb a neutron which carries no electric charge, and therefore faces none of the electrostatic repulsion that makes proton-on-proton fusion so difficult at anything less than stellar core temperatures. A neutron can approach a nucleus quietly and be absorbed. Once absorbed, it makes the nucleus heavier. If the new nucleus is unstable, it decays, converting one of its neutrons into a proton, and the element climbs one step up the periodic table. Repeat this process enough times, and you can build any element: copper, tin, barium, lead. In principle, all the way to uranium. There are two versions of this process, distinguished by how quickly the neutrons arrive. In the slow process, astronomers call it the S process. Neutrons arrive at a low rate, one at a time, with enough time between captures for any unstable nucleus to decay before the next neutron arrives. The nucleus climbs the ladder steadily, one rung at a time, never accumulating too many neutrons to decay safely. The slow process produces elements from just above iron up to lead and bismuth, threading through the stable isotopes of each element in turn. In the rapid process, the R process, neutrons arrive in such enormous quantities that nuclei are bombarded continuously, absorbing neutron after neutron faster than they can decay. A nucleus can accumulate far more neutrons than any stable configuration would allow. Only after the neutron flux stops do these enormously neutron-rich nuclei decay, cascading down into stable configurations that would have been unreachable by the slow path. The rapid process produces the heaviest elements: gold, platinum, uranium, and roughly half of all the elements heavier than iron. The slow process was identified theoretically in the 1950s. Its site was proposed: the interiors of dying low-mass stars, specifically the class of stars known as asymptotic giant branch stars, in the late stages of their lives when they alternately burn hydrogen and helium in shells around an inert core. These stars puff up, pulse, generate neutrons in their interiors, and dredge those neutrons up into layers where they can be absorbed by heavier nuclei. Eventually, the star sheds its outer layers entirely, leaving behind a white dwarf and dispersing its synthesized elements into the surrounding space. That shedding is worth picturing because it is gentler than a supernova and works on a different timescale entirely. A dying low-mass star does not explode. It swells into a vast, cool, bloated giant, becomes unstable, and over tens of thousands of years pushes its outer layers off in successive slow waves. Like a long exhalation, the expelled gas drifts outward, lit from within by the hot exposed core, forming the glowing shells that astronomers, through a long-standing misnomer, call planetary nebulae. They have nothing to do with planets. An early observer simply thought the round shapes resembled them. Inside, the bare core settles into a white dwarf and begins its multi-billion-year cooling. This is the path of the great majority of stars, the Sun among them. In roughly 5 billion years, our own Sun will do exactly this swell, grow unstable, shed its outer layers in slow shells carrying carbon and nitrogen and slow-process metals out into the galaxy, and leave behind a cooling white dwarf about the size of the Earth. The elements it disperses will, in some far future cloud, be available to build something else. The factory does not stop when one star dies. It hands its material to the next. This was a reasonable theory. The question, in the early 1950s, was whether it was true. And the evidence that it was true did not come from a theoretical calculation. It came from an element that should not have existed in the spectrum of a star at all. Technetium is element 43 on the periodic table. It sits between molybdenum and ruthenium, and it has a property that makes it unlike almost any other element you will encounter in a list of stellar abundances. It has no stable isotopes. Every form of technetium is radioactive. The longest-lived form has a half-life of around 4 million years. The form produced by the slow neutron capture process has a half-life of approximately 211,000 years. 4 million years is a long time by human standards. It is nothing by cosmic ones. The solar system is 4.6 billion years old. If any technetium had been present when the solar system formed, if it had been present in the gas cloud that collapsed into the Sun and the planets, it would have decayed away roughly 1,000 half-lives ago. There would be none left. No spectrograph looking at a star in our galaxy should, by any reasonable expectation, detect the signature of technetium because technetium formed in the early universe is long gone. Paul Merrill was 64 years old in the spring of 1952, and he had spent the bulk of his career at the Mount Wilson Observatory in California, attached to its 60-inch telescope as a spectroscopist, studying the light of unusual stars with a patience and precision that came from decades of practice. He was particularly interested in a class of cool, luminous red giants known as S-type stars, stars whose spectra showed distinctive patterns of zirconium oxide that set them apart from ordinary red giants. He had been the first to formally define that classification back in 1922. On the 2nd of May, 1952, he published a paper in the journal Science, reporting the detection of technetium absorption lines in the spectra of several of these stars, including the variable star R Andromedae. Merrill was initially cautious about his own result. The element he had found in these stars did not even exist naturally on Earth. It had been the first element produced artificially, synthesized in a particle accelerator in 1937, and its name, technetium, derived from the Greek word for artificial. To announce that you had found an artificial element in the spectrum of a star was not the kind of claim anyone made without hesitation. But the evidence was clear. The spectral lines were there. The wavelengths matched. And the only interpretation that made physical sense was the one that overturned a central assumption of astrophysics at the time. The assumption that all stars had essentially the same chemical composition and that this composition reflected what had been present since the universe began. If technetium was present in these stars present now, not as a residue of the Big Bang, but as a living, decaying, recently made element, then nuclear reactions inside those stars were producing heavy elements at this moment, not had produced, were producing. This was the first unambiguous, directly observed proof that stellar nucleosynthesis of heavy elements is an ongoing process, not a thing that happened once, at the beginning, and stopped. A thing that is happening now, inside specific stars that we can point a telescope at, in specific elements whose half-lives we can measure. It was also, quietly, the first direct evidence of the slow process. The technetium it produces is dredged up to the stellar surface and detected in the spectrum before it has had time to decay. The presence of technetium in a star's atmosphere is a kind of clock. You are seeing an element that was made recently enough to still be there. The clock runs at 211,000 years. The fact that the clock is still running means the factory is still running. It is hard now to recover how unsettling that was. For most of the history of astronomy, the chemical makeup of the stars had been treated as a given fixed, uniform, set once and unchanging, the same in every star because it had been the same since the beginning. Cecilia Payne had already shaken the assumption that stars were made of the same stuff as the Earth. Merrill's technetium shook something deeper. The idea that the inventory of elements was static at all. Here was an element with a short fuse, present in a star where it could not have survived from the beginning, which meant the star had made it recently, on its own, in its own interior. The periodic table was not a finished document handed down from the Big Bang. It was being written, still, in the cores of stars a person could point a telescope at on a clear night. A man of 64, in a domed building on a mountain in California, had looked at the light of a red giant and caught the universe in the act of manufacturing matter. The slow process, as the following decades of research confirmed, proceeds through a winding path up the periodic table, building most of the elements from just above iron through lead and bismuth. Dying low-mass stars are, in this sense, slow factories. Over the final stages of their lives, which can last millions of years, they quietly assemble heavy nuclei and eventually disperse them into the interstellar medium when their outer layers are shed. The calcium that formed your bones may have passed through one of these stars. A substantial fraction of the lead in the Earth's crust was built by the slow process in stars that lived and died before the solar system formed. Lead is an interesting case, in fact, because it has two origins separated by billions of years. Some of it is original, built by the slow process in ancient stars and folded into the Earth at its formation. But some of the lead in the ground today did not exist when the Earth formed. It is the stable endpoint of the long radioactive decay chains of uranium and thorium, which means it has been accumulating ever since, one atom at a time, as those heavy elements come apart. There is lead in the crust right now that was uranium a billion years ago. Both kinds, the ancient and the freshly arrived, are chemically identical, and both ultimately traced to events that made elements heavier than iron, by neutron capture, long before the sun. There is also a category of element in your body that comes from none of these processes, not the Big Bang, not stellar fusion, not neutron capture in either form. A small one, easy to overlook, but real, and it fills in a gap that the rest of the night's account would otherwise leave open. The elements are lithium, beryllium, and boron, three of the lightest in the periodic table, sitting just above hydrogen and helium. By rights, they should be common, given how light they are. They are not. They are among the rarest elements in the universe, far rarer than the much heavier carbon and oxygen that sit just beyond them. And the reason is a kind of double bind. The Big Bang made only the barest trace of lithium and essentially none of the others, because of the same mass 5 and mass 8 gaps that stopped nucleosynthesis at helium. And stars, rather than making these elements, destroy them. Lithium, beryllium, and boron are so fragile that they are consumed in the hot interiors of stars almost as fast as any process could build them. A star is, for these three elements, a furnace that eats them. So where did the lithium in your body come from, and the trace of boron? The answer is not a star at all. It is the empty space between the stars. The galaxy is filled with cosmic rays, atomic nuclei accelerated to enormous speeds, close to the speed of light, flung out by supernova shockwaves and other violent events, and then traveling through interstellar space for millions of years. When one of these high-speed nuclei, often a proton, strikes a heavier nucleus drifting in the interstellar medium, such as a carbon or oxygen nucleus, the collision can shatter the heavier nucleus into fragments. This is called spallation. The heavier nucleus breaks apart, and among the pieces are exactly the light nuclei that stars cannot make and the Big Bang barely made. Lithium, beryllium, boron. This is the only significant source of beryllium and boron in the universe, and a major source of the lithium. It does not happen in a star or in an explosion. It happens in the thin, cold, near-empty medium between the stars, one collision at a time, over billions of years, a slow accumulation of fragments knocked off heavier atoms by particles that have been traveling, in some cases, since before the solar system existed. The boron that exists in your body in trace amounts, contributing in small ways to the structure of your cell walls and your bones, was made not in a star but in a collision in deep space, when a cosmic ray that had been traveling for an unknowable length of time struck a heavier nucleus and broke it. That accounts for the light, fragile elements. The heaviest ones, the gold, the iodine, the uranium, require the opposite of a single quiet collision. They require the most violent few seconds anywhere in the universe. The slow process threads through the stable isotopes, which means it cannot build the most neutron-rich configurations. The heaviest elements, gold, platinum, uranium, and roughly half of everything heavier than iron, require the rapid process. And the rapid process requires something the interior of a dying low-mass star cannot provide. A neutron flux so enormous that nuclei are flooded with tens of neutrons before they have any opportunity to decay. The slow process operates in a gentle thermal environment over long timescales. The rapid process requires something closer to catastrophe. Where exactly that catastrophe occurs was, for most of the second half of the 20th century, one of the genuinely unsettled questions in nuclear astrophysics. The two main candidates were the cores of collapsing massive stars, the same core collapse supernovae that helped make the iron in your blood, and the merger of two neutron stars. Both environments are neutron-rich enough, in principle. Both are energetic enough, but nailing down which one was actually responsible, and in what proportions, required observational evidence that did not exist until very recently. To understand where the gold in your body comes from, it helps to understand what a neutron star is, because it is two of them, colliding, that made it. A neutron star is what remains when a massive star's core collapses, and the collapse stops just short of forming a black hole. The protons and electrons of the core are crushed together so violently that they merge into neutrons, and the entire core, once larger than the Earth, is compressed into a sphere roughly 12 kilometers across. 12 kilometers. You could drive across it in 10 minutes, on a surface that would not survive the drive, and neither would you. Into that small sphere is packed something between 1 and 2 times the mass of the Sun. Hold those two numbers next to each other. A city's width, more mass than the Sun. They do not reconcile easily. A single teaspoon of the material inside a neutron star would weigh something close to 1 billion tons, the mass of a mountain, in a volume that fits on a spoon. The surface gravity is so extreme that an object dropped from a height of 1 meter would strike the surface, having reached a speed of millions of kilometers per hour. This is not an exotic curiosity at the far edge of physics. It is the densest form of matter that can exist without collapsing into a black hole, and the universe makes them routinely every time a sufficiently massive star dies and the core stops just short of the brink. Now imagine two of them, bound in orbit around each other, two collapsed stellar cores, each more massive than the Sun, each the width of a city, circling. Over millions of years the orbit decays. They spiral inward, faster and faster, until in the final second they are whipping around each other hundreds of times per second, and then they touch. The collision releases, in an instant, a flash of energy that briefly rivals everything. It throws off a fraction of a sun's worth of neutron-rich matter, and it floods that matter with the most intense burst of free neutrons anywhere in the cosmos. That is the rapid process. That is where the heaviest elements are made: gold, platinum, uranium, the iodine in your thyroid, in the few seconds after two dead stars collide. This was the event we had theorized for decades and never caught in the act. Then we did. It arrived in the early morning hours of the 17th of August, 2017, in the form of a ripple in space-time that had been traveling for approximately 130 million years. The gravitational wave detectors operated by the project known as LIGO, two large-scale instruments in the United States, one in Louisiana and one in Washington state, had been operational in their upgraded form for less than 2 years when they registered the signal. A third detector, called Virgo, in Italy, picked it up as well. The signal was different in character from the mergers of two black holes that these instruments had detected in the previous 2 years. It was longer, slower, and its properties indicated that the objects producing it were not black holes but neutron stars, each between approximately 1 and 2 times the mass of the Sun, spiraling into each other. 1.7 seconds after the gravitational wave signal ended, 1.7 seconds after the merger itself, the Fermi Gamma-Ray Space Telescope detected a burst of gamma rays from the same direction in the sky. The gamma rays were expected. A short gamma ray burst a brief, intense flash of high-energy radiation. Lasting less than 2 seconds had been theorized for decades to be the electromagnetic signature of a neutron star merger. This was the first time the theory could be tested directly, because this was the first time a merger had been detected in gravitational waves first and localized accurately enough for follow-up observations. Within hours, telescopes around the world were pointing at a galaxy roughly 130 million light-years away, in the constellation Hydra, a galaxy listed in the astronomers' catalogues simply by a number. Some 70 observatories, across every band of the electromagnetic spectrum, turned toward the same point of sky in the same day. What they found there was a new point of light that had not been present in any prior image of that galaxy. A kilonova, a transient event powered by the radioactive decay of freshly synthesized heavy elements, glowing first in blue-white optical light, and then shifting over days toward the infrared as the newly made material expanded and cooled. The spectra were what mattered. What the Gemini Observatory, the European Southern Observatory's Very Large Telescope, and the Hubble Space Telescope recorded in the light of that kilonova were the signatures of heavy elements in the lanthanide series, the dense, neutron-rich elements that are characteristic products of the rapid process. The opacity of the expanding material, the color evolution, the rate of brightening and fading, all of it was consistent with the synthesis of large quantities of elements, far heavier than iron, in the seconds following the merger. Gold, platinum, barium, the elements whose production had been theorized for decades but never directly witnessed. The quantity of gold produced in that single event is difficult to pin to a precise figure. Different analyses of the kilonova light yield different estimates, and the uncertainties are substantial, but the range runs from something in the vicinity of several Earth masses to tens of Earth masses, depending on the model applied. What is not in dispute is that the quantity is large, that the identification of rapid process elements in the spectrum is secure, and that the event was, by direct observation, a neutron star merger. This was not a small confirmation. For the first time, there was an observed event with a gravitational wave detection, a gamma-ray burst, an optical kilonova, and spectroscopic identification of the products that connected a specific astrophysical site to the production of the heaviest elements. The rapid process was happening here. In this galaxy, 130 million years ago, not long after the dinosaurs appeared on Earth, and we detected the gravitational waves from it and followed them to a kilonova and watched the gold cool. There was a second result folded into that 1.7 seconds. The gravitational waves and the gamma rays had both traveled the same 130 million light years, and they arrived within less than 2 seconds of each other. That near simultaneity, after so vast a journey, showed that gravity and light travel at the same speed to a precision nothing else could have provided. A fundamental fact about the universe, confirmed as a side effect of watching two dead stars collide. And the event marked the beginning of something practical. For the first time, the same cosmic event had been observed in gravitational waves and across the full range of light by some 70 observatories on the ground and in space, all turned to the same point of sky within a single day. Astronomers had spent the whole history of the science studying the universe through light alone. Here, for the first time, they had felt an event through the shaking of space-time itself, and then looked at it as well, and the two accounts agreed. The merger answered something that had been open since the slow and rapid processes were first proposed in the 1950s. The rapid process happens in neutron star mergers. It had been predicted, now it had been seen. The story is not entirely closed, and it is worth saying so clearly. Neutron star mergers are confirmed as a site of the rapid process. But whether they account for all of the rapid process material in the universe, every atom of gold, every uranium nucleus remains an open question. The timing is one issue. Neutron star mergers take a long time to occur after the stars that produce the neutron stars have died, and some of the oldest, most metal-poor stars in our galaxy show enrichment in heavy elements at a level that is difficult to explain if mergers were the only source, and they take as long as models suggest. There may be other sites operating on shorter timescales, certain kinds of massive star collapse, or objects called magnetars, which are neutron stars with magnetic fields so intense that they occasionally release flares energetic enough to eject neutron-rich material. A calculation published in 2024 proposed that giant magnetar flares could contribute meaningfully to the inventory of heavy elements. The debate is ongoing, but the central fact that neutron star mergers are a real, observed, confirmed source of the heaviest elements is established. The merger of 2017 is the evidence. The periodic table has a postmark now. Not a single one, but several. Hydrogen carries the postmark of the first 3 minutes. Carbon and oxygen carry the postmark of stellar interiors. Iron carries 2 postmarks at once: the collapse of a massive star and the detonation of a white dwarf. Lithium and boron carry the strange postmark of empty space, of a cosmic ray striking a heavier atom and breaking it. And gold and iodine carry the postmark of 2 dead stars colliding. Each was discovered separately over nearly a century. None was obvious in advance. Several were actively resisted when they first appeared. What it looks like when you map those postmarks onto a single human body is the subject that comes next. Everything tonight has described the Big Bang, the fusion in stellar cores, the deaths of massive stars, the detonation of white dwarfs, the collisions of neutron stars, the slow grinding of cosmic rays against atoms in deep space produced material and scattered it into the space between the stars. But scattered material is not a body. There is a gap in the story that has to be crossed. How did all of that dispersed matter, made in so many different events across so many billions of years, come together into one place, into a sun, a set of planets, an Earth, and eventually into something lying in the dark? The answer begins with a cloud. Roughly 4.5 billion years ago, in an unremarkable region of the Milky Way, there was a cold, dark cloud of gas and dust, mostly hydrogen and helium left over from the Big Bang, salted through with the heavier elements that earlier generations of stars had made and shed. This is the crucial point. The cloud was not primordial. It was enriched. Every carbon atom, every oxygen atom, every grain of iron-bearing dust in that cloud had been made in a star or an explosion that lived and died before the sun existed. The cloud was a graveyard and a nursery, at once the dispersed remains of dead stars, waiting to become a new one. Something disturbed it. A cloud like this can drift for a very long time without collapsing, held up by its own internal pressure and gentle turbulence. But if it is compressed by a passing shockwave, for instance, it can begin to fall inward under its own gravity, and once it begins, it does not stop. There is direct evidence, locked inside the oldest rocks in the solar system. For what did the compressing? When meteorites that formed in the earliest days of the solar system are analyzed, they are found to contain the decay products of certain radioactive isotopes, with very short half-lives among them, a form of aluminium that decays away in under 1 million years. For those isotopes to have been present in the forming solar system at all, they must have been made very shortly before it formed within 1 million years or so. And the events that make them in quantity are supernovae. The presence of their decay products in the most ancient meteorites is a fingerprint. A massive star died nearby, just before the sun was born, and its shockwave may well have been the push that started the cloud collapsing while its freshly made elements were stirred into the mix. The collapse, once underway, concentrated most of the cloud's mass at the center, where pressure and temperature climbed until hydrogen fusion ignited and the sun switched on. The leftover material, flattened by its own rotation into a disk around the new star, began to clump dust grains, sticking to dust grains, pebbles to pebbles, boulders to boulders, until bodies large enough to pull in their neighbors by gravity swept up the rest and became planets. The Earth assembled this way, out of the enriched dust of the disk, somewhere around 4.5 billion years ago. Every element discussed tonight was in that disk: the hydrogen from the Big Bang, the carbon and oxygen and nitrogen from earlier stars, the iron from supernovae and white dwarf detonations, the lithium and boron chipped from heavier atoms by cosmic rays, the gold and iodine from neutron star mergers that had occurred somewhere in the galaxy's past. All of it, gathered from events separated by billions of years and unimaginable distances, mixed together in a single rotating cloud and folded into the rock and water and air of a single planet. And then, on that planet, over the following 4 billion years, chemistry became biology, and the elements were taken up and arranged and rearranged through every living thing that ever existed, passed from soil to plant to animal and back, again and again, until a particular subset of them, 7 octillion atoms of it, was assembled, temporarily, into the body that is lying here now. That is the bridge. The events made the material. The cloud gathered it. The earth held it. Life arranged it. And the arrangement, for the length of one human life, is you. There is a way of looking at a body that most of us never try. Not the biological way, the organs and systems and the chemistry that keeps them running. A different way, further back, further out. The way that asks not what your body is doing right now, but where it came from, in the deepest sense of where. Not which country, not which parents, not which evolutionary lineage, where the actual material came from. The atoms themselves. If you tried to map that, if you took every element in an adult human body and traced each one back to the event that produced it, what you would get is not a single origin story. You would get six separate categories of cosmic event, each responsible for a different portion of what you are, each occurring in a different kind of place, each separated from the others by enormous gulfs of time. Jennifer Johnson, an astronomer at Ohio State University, made exactly this map in 2017. She and a colleague were at a conference, she later said, and should probably have been paying attention to the talks. Instead, they produced a color-coded periodic table, on paper, with markers, assigning each element to the process or processes responsible for it. 6 colors for 6 origins: Big Bang fusion, cosmic ray collisions, dying low-mass stars, exploding massive stars, merging neutron stars, and exploding white dwarfs. The table has been reproduced widely since, because it does something that no amount of prose explanation quite manages. It makes the diversity of origins visible at a glance. You can see that hydrogen is one color, and iron is another, and gold is a third, and that the colors are not smoothly distributed but clustered by the physics of each process. What follows is a slower pass through what that map means for a specific body. The one lying here, now, in the dark. Begin with water. The human body is roughly 60% water by mass. Water is a molecule of 2 hydrogen atoms and 1 oxygen atom, and those 2 elements have entirely different origin stories. The oxygen in the water in your cells was made in the interior of a massive star and scattered into space when that star died. The hydrogen in that same water molecule is incomparably older. It formed in the first 3 minutes after the Big Bang, nearly 14 billion years ago, and has never been inside a star at all. When you drink a glass of water, the oxygen in it is billions of years old, but was forged in a stellar core. The hydrogen in it is nearly as old as the universe, and was forged before any star existed. 2 atoms, bonded together into a single molecule, different ages, different birthplaces, one from a stellar explosion, one from the beginning of time. This is the texture of you. At the atomic level, move to the carbon. Carbon is the structural backbone of biology. Every major category of molecule that biology uses, proteins, carbohydrates, fats, the nucleic acids that carry your genetic information, is built on a carbon framework. Carbon makes up about 18% of your body by mass. In a body of 70 kilograms, that is somewhere in the neighborhood of 600 billion trillion carbon atoms, a number large enough to be meaningless as a number, but each one with a traceable history. Each one was assembled 3 helium nuclei at a time, through the resonance Fred Hoyle insisted must exist. The carbon in your DNA is there because that resonance is there. Most of the carbon in you came from stars that ended their lives quietly rather than violently low mass. Stars that, in their final stages, pulsed and expanded and shed their outer layers in slow outflows, dispersing their contents into the surrounding space. Some carbon also came from the outer layers of more massive stars expelled in supernova shock waves. However it was dispersed, all of it was forged in a stellar core, hot enough for 3 helium nuclei to combine before the intermediate steps fell apart. The nitrogen in you, in your DNA, in the amino acids that make up your proteins, was produced primarily in the carbon-nitrogen-oxygen cycle running in the cores of stars more massive than the Sun, where carbon acts as a catalyst and nitrogen is an intermediate product. It too came from stellar interiors and stellar deaths, the same broad category of events as the carbon and oxygen. Nitrogen is worth a second look because of a peculiar fact about how your body has to get it. Roughly 4/5 of the air you breathe is nitrogen. It is the most common gas in the atmosphere by a wide margin, far more abundant than the oxygen you actually use, and yet your body cannot touch it. Atmospheric nitrogen exists as two atoms locked together by one of the strongest bonds in chemistry, so tightly bound that breaking it apart takes more energy than your cells can spare. You inhale this nitrogen with every breath and exhale all of it, unused. The nitrogen that is actually built into your proteins and your genetic material had to be pried out of the air by other organisms, first by bacteria in the soil and by the roots of certain plants, which have the specialized machinery to break that bond and pass usable nitrogen up the food chain to you. So the nitrogen in your DNA was forged in a massive star, scattered by its death, gathered into the earth, locked into the unbreakable gas of the atmosphere, and then liberated from that gas, one molecule at a time, by living things equipped to do what your own cells cannot. Now go to the calcium. The calcium in your bones and teeth, about 1 kilogram in a typical adult body, was produced in the silicon-burning stage of a massive star's life, in the final days before core collapse. Silicon burning runs at temperatures exceeding 3 billion degrees Celsius and produces a range of elements clustered around iron in the periodic table. Chromium, manganese, iron, cobalt, nickel, and calcium. These are the iron peak elements, produced in a star that is already counting its last hours. When the star explodes, these elements are scattered into the surrounding space, drift through the interstellar medium for billions of years, and eventually settle into the rocks and oceans of a forming planet where, in the case of your calcium, they entered the food chain and worked their way through billions of years of evolving life until they reached the organisms that became you. There is calcium's quiet partner to consider as well: phosphorus. Phosphorus is one of the 6 elements that make up 99% of you, and it is arguably the one that life can least afford to be without. The backbone of the DNA molecule, the 2 long rails of the twisted ladder that carries your genetic information, is built from alternating sugar and phosphate units. The molecule that carries usable energy around inside every one of your cells is held together by phosphorus bonds and spends it by breaking them. Your bones and teeth are, chemically, largely a mineral of calcium and phosphorus. Take phosphorus out of biology, and there is no genetics, no energy currency, no skeleton. There is no life of the kind we know. And yet phosphorus is cosmically scarce. It is not among the easy products of stellar fusion the way carbon and oxygen are. It is made in massive stars, in the late burning stages, and dispersed by supernovae, but in modest amounts, far less abundant than the carbon and oxygen and iron around it. On the cosmic ledger, phosphorus is rare in a way that the chemistry of life is not. Life uses it lavishly. The universe makes it sparingly. This has become a genuine open question in the study of whether life is common elsewhere. If phosphorus is in short supply across the galaxy, and if it is unevenly distributed, concentrated in some regions and absent from others, then the raw material for life may be rarer than the more famous ingredients, water and carbon, would suggest. Recent work tracing where phosphorus is produced and how it travels into the clouds that form planets has tried to map how much of it is actually available and where. The results are not yet settled. It remains possible that phosphorus, rather than water or carbon or energy, is one of the tighter bottlenecks on life, and that the comfortable amount of it built into your own cells reflects a piece of cosmic good fortune in where and when the solar system happened to form. For now, the phosphorus in your DNA and your bones and your every cellular transaction was made, like the calcium beside it, in the dying stages of massive stars, and scattered by their explosions, and gathered into the cloud that became the Earth. It is simply rarer than almost everything else you are made of. The iron follows the same broad path, with the added twist established earlier in the night. Some of it came from the collapse of a massive star, and most of it, statistically, from the detonation of a white dwarf. The iron in your hemoglobin did not drift gently from anywhere. It came from an explosion. Which explosion we cannot say for any single atom. It is worth noting why life reached for iron in particular, of all the elements an explosion could have provided. Iron has a chemical property that is close to ideal for the job your blood needs done. It can bind an oxygen molecule firmly enough to pick it up in the lungs, yet loosely enough to let it go again in the tissues that need it. That reversible grip is the whole basis of breathing at the cellular level. Each molecule of hemoglobin cradles 4 iron atoms, and each iron atom holds 1 molecule of oxygen for the length of a single trip through the body, before releasing it and returning for another. A single red blood cell carries hundreds of millions of these hemoglobin molecules. The color of your blood and the rust red of iron oxide and the reddish cast of Mars and the faint red of certain stars all trace back to the same atom and the way it interacts with light and with oxygen. Life did not invent iron's usefulness. It inherited it from a supernova or a detonating white dwarf and built a body around it. Consider, too, what your body is dissolved in. The fluid inside and around your cells, your blood plasma, the water in your tissues is salt water, held at a concentration not far from that of seawater. And it has to be because the chemistry of life as it first arose was the chemistry of the ocean. The salt is mostly sodium and chlorine, the two elements that combine to make ordinary table salt, and your nerves and muscles depend on moving sodium across cell membranes, just as they depend on potassium. The signal that is running down a nerve in your hand as you adjust your position right now is, at bottom, sodium and potassium atoms crossing a boundary and crossing back. Both of those elements were made in massive stars. Sodium is produced in the carbon burning stage, when the carbon left over from helium burning fuses at higher temperatures, chlorine in the later oxygen burning stage and in the explosion itself. Then they were scattered, gathered into the earth, dissolved into its oceans, and taken up by the living things that arose there, which is why, hundreds of millions of years after the first animals left the sea, you still carry a measure of that ancient ocean inside you, made of atoms forged in stars, and kept at very nearly the saltiness of the water life began in. Now go further out on the periodic table, into the region fusion cannot reach. Iodine is element 53. It is not an element most people think about, unless they are thinking about thyroid function. But the thyroid depends on iodine absolutely. It is incorporated into the hormones that regulate metabolism throughout the body. An adult body contains approximately 25 milligrams of iodine, most of it in the thyroid. 25 milligrams is a small amount. It is enough to cause serious problems if absent, which is why iodine deficiency was historically one of the most common preventable causes of developmental problems worldwide, before the introduction of iodized salt in the 20th century. Those 25 milligrams of iodine are rapid process elements. The only stable form of iodine is too neutron-rich to be reached efficiently by the slow path it requires the flood of neutrons in the seconds following a neutron-star merger. The iodine in your thyroid was made in the collision of two dead stars. There is no way to say which collision, no way to date it, the way a geologist can date a rock. What can be said is that the iodine arrived in the interstellar medium well before the solar system formed 4.6 billion years ago, was incorporated into the early Earth, along with the rest of the heavy elements, and made its way through geochemical and biological cycles into the food you eat. And the gold. Gold is element 79, deep in the rapid process region of the periodic table, unreachable by fusion and reachable by the slow process only at the very margins. The gold that exists in your body, and there is gold in every human body, roughly 0.2 milligrams on average, distributed through the blood and tissues, came from a neutron star merger. Gold is rare for a reason that traces directly to how it is made. Because it can only be produced in the rarest and most violent events the universe stages, it is genuinely scarce everywhere. Scarce in the galaxy, scarce in the Earth, scarce in you. All the gold ever mined in human history, melted together, would form a single cube only around 20 meters on each side, and much of what the Earth received sank into the molten core during the planet's formation, beyond any reach. A good deal of the gold we can actually get at was delivered later, by impacts, after the crust had solidified. Every gram of it, wherever it sits now, began in the collision of two dead stars before the sun existed. 0.2 milligrams. It is not very much. It would form a cube smaller than a grain of salt. But it is there, and it has a history that goes back to a collision between two stellar corpses that occurred before the Earth existed, releasing gravitational waves, producing a kilonova, scattering elements that eventually settled into the cloud that formed the solar system, and then, through a chain of geological and biological processes spanning billions of years, arrived here, lying in this body, in the dark. There is one element worth naming before leaving the body that is different from all the others, because it is not inert. it is still going off. Your body contains potassium, an element essential to every nerve impulse and every heartbeat. The signal that travels down a nerve and the contraction that follows it both depend on potassium crossing the membranes of your cells. Most of that potassium is ordinary and stable, but a small, fixed fraction of all the potassium in the universe is a radioactive form with a slightly heavier nucleus, and it is unstable. It decays, with a half-life of roughly 1.25 billion years, releasing a particle of radiation each time it does. That radioactive potassium is inside you. It is in your muscles, your blood, your bones, wherever potassium goes. And because it is there, your body is very slightly radioactive, and always has been, and so is everyone else's. Inside an average adult, this potassium alone is decaying at a rate of several thousand atoms every second. Right now, as you lie here, somewhere between 4,000 and 5,000 potassium nuclei are coming apart inside you each second, each one a small event left over from the deep past. Because here is where that potassium came from. Radioactive potassium is made in massive stars and scattered by supernovae, like the iron and the calcium. With a half-life of more than 1 billion years, the radioactive potassium that was folded into the Earth 4.5 billion years ago has only partly decayed a few half-lives, no more. The radioactive potassium decaying inside your body tonight is original material, made in a dying star before the solar system existed, still ticking down inside you, in real time, at a rate you could measure with the right instrument held against your skin. A small piece of stellar debris, not yet finished decaying, doing the last of its decaying in you. There is a second source of it, fainter still, and it connects back to the cosmic rays from earlier tonight. High in the atmosphere, those same cosmic rays strike nitrogen and produce a heavy, radioactive form of carbon. Plants absorb it from the air. You eat the plants, and so a tiny, constant trace of radioactive carbon is built into your tissues throughout your life, the same isotope that, once a living thing dies and stops replacing it, allows archaeologists to date what remains by measuring how much is left. While you are alive, you carry a fresh supply, manufactured overhead by particles that have traveled across the galaxy. You are not, in any sense that matters, dangerously radioactive. The amounts are tiny and entirely natural. But it is worth holding the fact plainly. There is material in your body, made in a supernova billions of years ago, that is still in the process of coming apart, and there is other material, made just above your head by a cosmic ray, doing the same. The events that built you did not all finish. Some of them are still happening, quietly, inside the body lying in the dark. Below the level of the 6 main elements, there is one more layer to name. A set of metals present in your body in only trace amounts: zinc, copper, manganese, cobalt, molybdenum, a few others that the chemistry of life cannot run without. They are cofactors, atoms held at the heart of enzymes. Where they do work, the surrounding protein cannot, grabbing and releasing other atoms, shuttling electrons, holding molecules in the precise geometry a reaction requires. There is cobalt at the center of the vitamin your nerves and blood depend on. There is zinc in the proteins that read and copy your DNA. There is copper in the enzymes that let your cells use oxygen at all. Remove any one of them, and specific, essential machinery stops. These metals sit just above iron on the periodic table, or scattered through the region beyond it, which means they were not made by the main fusion chain. They came from the slow neutron capture process in dying low-mass stars, from the explosions of massive stars, and the heavier ones from the rapid process in collisions and catastrophes. The same channels traced across tonight, producing not just the bulk material of your body, but the rare metallic atoms tucked into its working parts. It is a strange inventory when you lay it out, a body running on hydrogen from the beginning of time and oxygen from exploded stars, a skeleton mineralized with supernova calcium and scarce phosphorus, blood carrying iron from 2 different kinds of stellar death, enzymes built around single atoms of metals forged by neutron capture, a thyroid holding iodine from a neutron star merger, and a few milligrams of merger-made gold distributed through the whole arrangement for no biological reason at all. Not one of those elements was made in the same place. Not one was made for this. And all of them are here, in working order, in the dark. The mapping is not uniform. It is not as if every element in you came from the same era or the same class of event. The hydrogen is the oldest, nearly 14 billion years. The carbon and oxygen are somewhat younger, produced in stars that lived and died before the solar system existed. The iron and calcium came from explosions of two different kinds. The lithium and boron were chipped off heavier atoms in the dark between the stars. And the gold and iodine came from collisions whose timing is harder to pin down, but which certainly preceded the formation of the Earth. You are not the same age throughout. Different parts of you are older than others. The hydrogen in your water is nearly as old as time. The origin of the iron in your blood was only confirmed by direct observation in 1987. The origin of the gold in your tissues was only confirmed in 2017. The question that opened tonight, how anyone ever worked out which atom came from where, given that the periodic table does not come with a postmark, has now been answered across nearly a century of observation, from Cecilia Payne identifying the composition of stars in 1925, through Paul Merrill's detection of technetium in 1952, through the neutrino burst from the supernova of 1987 to the kilonova of 2017. Each of those discoveries added a piece of the map. Several were actively resisted when they first appeared. The map is now largely complete, but largely is not entirely. There are places on it where the color assignment is still uncertain, where the evidence points in a direction but does not arrive at a definitive answer. And underneath all of it, there is the larger question of the theoretical framework that assembled everything known about element production into a single coherent account, and what happened to the man who did most of the foundational work but did not receive the recognition the work deserved. That is where tonight goes next. In 1957, a paper was published in the journal Reviews of Modern Physics under the title Synthesis of the Elements in Stars. It ran to 104 pages. Its 4 authors were listed in alphabetical order: Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle. In the language of scientific publishing, this meant Margaret Burbidge was first author, a detail worth noting, because her name often gets displaced in popular accounts in favor of the male colleagues with higher institutional profiles. The paper is known almost universally by the initials of its 4 authors. It is one of the most cited papers in the history of astrophysics, and its core framework, the identification of the nuclear processes responsible for building the elements in stellar interiors and stellar depths, remains the foundation of the field today. 8 processes were identified and named: the proton-proton chain and the carbon-nitrogen-oxygen cycle for hydrogen burning, the triple alpha process for helium burning, the slow and rapid processes for neutron capture, several others for specific cases and specific isotopes. The paper drew together into a single coherent account work that had been accumulating across several fields for years: the nuclear physics data that Fowler's laboratory had been measuring, the stellar abundance observations that Margaret Burbidge had compiled from telescope work, and the theoretical architecture that Fred Hoyle had been building since his papers of 1946 and 1954. It is worth pausing on Margaret Burbidge, because the observations she contributed were obtained against an obstacle the other 3 authors never faced. The largest telescope in the world available to the collaboration was the Great Instrument at Mount Wilson, and later Palomar and those telescopes did not admit women. The dormitory where observers slept during long nights of work was for men. When Margaret Burbidge needed telescope time, she obtained it by applying in her husband Geoffrey's name and presenting herself, in effect, as his assistant, observing through the night on instruments she was formerly not permitted to use, gathering the stellar spectra that became part of the foundational paper of the field. The data on element abundances in stars, which anchored the whole framework to reality, came in significant part from a scientist who had to disguise her own access to the sky in order to collect it. A Canadian physicist named Alastair Cameron, working independently at the Chalk River Laboratories in Ontario, published a parallel theoretical account in the same year, arriving at many of the same conclusions by a largely independent route. Cameron's paper receives less attention in popular accounts than the 4-author paper, but the two together represent the completion of a theoretical framework that Cecilia Payne's discovery had made necessary and that Paul Merrill's technetium had confirmed was real. In 1983, the Nobel Prize in Physics was awarded jointly to William Fowler and Subramanian Chandrasekhar, Fowler received his half for his theoretical and experimental studies of the nuclear reactions of importance in the formation of the chemical elements in the universe. Chandrasekhar received his for his theoretical work on the structure and evolution of stars, including the calculation of the mass limit that bears his name. Fred Hoyle received nothing. The astronomical community's response to this was, in the words of people who were there, one of widespread disbelief. Fowler himself, in various interviews and writings, was consistent and clear about where the foundational ideas had come from. He had said that the grand concept of nucleosynthesis in stars was first definitely established by Hoyle in 1946, not in 1957. 1946, before the four-author paper, before Merrill's technetium, before the Caltech experiments. Hoyle had proposed the theoretical framework and then spent a decade building the evidence for it. Geoffrey Burbidge, reflecting on the Nobel decision in later years, argued that a major reason for Hoyle's exclusion was that Fowler had been assumed, incorrectly, to be the intellectual leader of the collaboration, a perception shaped partly by the fact that Fowler was an experimental physicist with a large, well-funded laboratory, while Hoyle was a theorist whose most important contribution predated the collaboration. If the prize was for the work the four of them had done together, the omission of the work's intellectual architect was striking. There were other possible reasons, and they have been discussed extensively by historians of science. Hoyle had spent decades as an outspoken opponent of the Big Bang theory, arguing instead for a steady-state cosmology in which the universe has no beginning and matter is continuously created to maintain a constant density. By the early 1980s, the steady-state theory had been ruled out by the evidence, and Hoyle had been wrong about it for a long time, and loudly. He had also publicly criticized the Nobel Committee in 1974, when the prize for the discovery of pulsars was awarded to Anthony Hewish, but not to Jocelyn Bell Burnell, the graduate student who had actually detected the first pulsar. Whether that criticism influenced a committee he would later need to impress is a question that cannot be answered from the public record. What can be said is that Fred Hoyle coined the term Big Bang, intending it as a dismissal, on a 1949 radio broadcast, that the theory he was dismissing turned out to be correct, that the nucleosynthesis framework he built, which required the Big Bang to have produced the lightest elements and left everything heavier to stars, is now the accepted account, that the carbon resonance whose existence he predicted, and Fowler's laboratory confirmed, bears his name in the scientific literature to this day, and that he died in 2001, having received the Crawford Prize, the Royal Medal, and the Gold Medal of the Royal Astronomical Society, but not the Nobel. The map of where the elements come from is his map, more than any other single person's. The recognition of that fact has been uneven, now, the blanks on the map, because a map that is mostly complete and a map that is complete are different things, and the gaps matter. The lithium problem is perhaps the most discussed. Big Bang nucleosynthesis predicts a specific abundance of lithium in the early universe, a ratio of lithium to hydrogen that follows from the same calculations that successfully predict the helium abundance to within a fraction of a d6%. But measurements of lithium in the oldest, most metal-poor stars in the Milky Way stars that formed early enough to carry something close to the primordial abundance consistently find lithium at roughly 2 to 3 times less than the predicted value. Not a small discrepancy. 2 to 3 times is significant. The explanation remains open. One possibility is that the old stars have destroyed some of their surface lithium over their long lives. Lithium is relatively fragile and can be depleted by the mixing of stellar material into hotter interior layers. Another is that the measurements themselves carry systematic errors that have not been fully accounted for. A third, more radical possibility is that the Big Bang nucleosynthesis calculations are missing something, some process, some particle, some piece of physics not yet included in the standard model that altered the lithium abundance in the early universe. None of these explanations has been confirmed. The lithium problem has been discussed in the literature for decades and is still discussed now. The question of the rapid process site is similarly open at the margins. Neutron star mergers are confirmed, but the timing problem, the difficulty of explaining the enrichment of the very oldest, most metal-poor stars if mergers are the only site, and take as long to occur as models suggest, has not gone away. The magnetar flare hypothesis proposed in 2024 adds a potential fast-acting, early universe source. Whether it operates at the scale required is still being worked out. There is also a way the heavy elements let us read the age of things, and it deserves a mention because it answers a version of tonight's opening question: how do we date any of this using the elements themselves? Some of the heaviest elements made by the rapid process are radioactive, with half-lives measured in billions of years, certain forms of uranium and thorium among them. When astronomers find very old stars in the outer halo of the galaxy stars that formed early in cosmic history, when heavy elements were still scarce, they can sometimes measure how much uranium or thorium those stars still contain, compared with stable, rapid process elements made alongside them. Because the radioactive ones decay at a known rate and the stable ones do not, the ratio between them works as a clock. The more the radioactive elements have decayed relative to the stable ones, the older the material must be. This technique has produced age estimates for some of the oldest stars in the galaxy of well over 12 billion years, consistent with a universe approximately 13.8 billion years old. It is the same principle that dates a rock or a bone, applied to starlight, reading the age of an element from how far it has come apart since it was made. And the same uranium and thorium sit in trace amounts inside the Earth, where their slow decay is one of the sources of heat that keeps the planet's interior molten and its continents moving. The rapid process that made the gold in your body also made the uranium that warms the ground beneath you. The same kind of event, a different element, still doing work billions of years later. And there are smaller uncertainties distributed across the periodic table elements, whose assigned color on Jennifer Johnson's table carries a question mark at the margin where two processes could contribute, and the relative proportions are not settled. Barium, strontium, europium, elements that sit in the transition zone between the slow process and rapid process domains, and whose precise production histories are still being constrained by observations of metal-poor stars and neutron star merger spectra. What this means, for the body lying here in the dark, is that the map of your own origins is almost complete, not entirely. The inventory runs to about 99% of what you are, with confident assignments. The remaining fraction sits at the frontier of what the field currently understands. There is a deeper frontier underneath the whole account, worth naming before tonight closes the historical thread. Every heavy element in you was made in a star or a stellar event, but the very first stars could not have been. The cloud that formed the sun was enriched by earlier generations of stars. Those earlier stars were enriched by ones before them, and following that chain backward, you arrive at a first generation that formed out of nothing but the hydrogen and helium of the Big Bang, with no heavier elements at all. These first stars had no carbon, no oxygen, no iron to begin with. They had to make the first heavy elements from scratch, and seed the universe with them, so that every later star and eventually the sun, and eventually you would have anything heavier than helium to be built from. We have never seen one. Not one. These first stars are thought to have formed within the first few 100 million years after the Big Bang, to have been very massive and very hot, and to have lived and died quickly, scattering the first carbon and oxygen and iron into a universe that until then had none. But because they were so short-lived and so distant in time, none survives today, and their light has had to cross nearly the whole age of the universe to reach us. They remain a prediction rather than an observation, one of the last major pieces of the element story that has not been directly confirmed. The James Webb Space Telescope, peering further back toward that early epoch than any instrument before it, is among the tools now searching for their signatures in the faint light of the earliest galaxies. If the first carbon in the universe, the ancestor of the carbon resonance that made every carbon atom since, was forged in those vanished stars, we have not yet caught the light that would prove it. You are mostly explained. The explanation took a century. It required Cecilia Payne being overruled and vindicated. It required Paul Merrill finding an element that should not exist. It required Hans Bethe working out the furnace. It required Fred Hoyle betting that a nuclear resonance he had never measured must be there. It required 20 particles from a dying star to pass through 2 underground tanks of water and be counted. It required a gravitational wave to cross 130 million light-years and shake an instrument's mirrors by a fraction of the width of a proton. Each of those things happened. The explanation, built from all of them together, is that the atoms in your body are a physical record of the universe's history, not metaphorically, but literally. The history is there, in the material. What it feels like to hold that, what it means to lie here, and understand that this body is an assembly of events spread across billions of years, is where tonight ends. There is a version of this story that could be told as triumph, a clean arc from ignorance to knowledge, from assumption to evidence, from the first guesses about what stars were made of, to a color-coded periodic table that assigns every element to its source. 100 years of work resolving into a complete picture. That version is not wrong, exactly. The picture is largely complete. The work is real. But it leaves something out that the actual history contains in abundance, which is how much resistance each piece of the picture met before it was accepted, and how long it took for the people who found the pieces to be recognized for finding them. Cecilia Payne disowned her own correct result in print, and spent decades in institutional obscurity before the field acknowledged what she had done. Margaret Burbage gathered the stellar spectra that anchored the foundational paper of her field by applying for telescope time in her husband's name. Because the observatory would not admit a woman, Paul Merrill found an element that by every prior assumption should not have been there, and was cautious enough about his own observation that he listed his correct interpretation as one of several possibilities, rather than stating it as the conclusion it was. Fred Hoyle spent the last decades of his life carrying the knowledge that the framework he had built had been given a Nobel Prize from which his name was absent, while the laureate who received the prize for that work had publicly named him as the field's founder. The history of this particular piece of science is not a history of smooth progress. It is a history of correct conclusions being delayed, disputed, and sometimes credited to the wrong person, interspersed with moments of extraordinary precision, a resonance predicted from the mere fact of carbon's existence, and found almost exactly where predicted, a stellar death detected in 2 different kinds of radiation at once, a gravitational wave followed within hours, to a glowing cloud of freshly made gold. What that history produced is a map. The map is what matters now. And what the map shows, when you look at it honestly, is something stranger than the simple version suggests. It does not show that you are made of stardust in the general sense that became a kind of cultural shorthand after Carl Sagan used the phrase. It shows something more specific and, in certain ways, more disorienting. It shows that you are made of several different kinds of cosmic event, each occurring at a different time, each operating by a different mechanism, and that these events are not interchangeable. The hydrogen in you was never inside a star. The carbon in you required a specific nuclear resonance that could in principle have been at a slightly different energy. The iron in you required either a massive star to collapse or a white dwarf to detonate. The boron in you required a cosmic ray to shatter a heavier atom in empty space. The gold in you required 2 dead stars to find each other across the dark and collide. These are not the same story told at different scales. They are genuinely different stories, happening in genuinely different places, producing genuinely different material, and all of it ended up through processes of dispersion and accumulation and chemistry and biology, spanning billions of years in one body. The question of what to do with that knowledge is not a scientific question. Science produces the map. What you bring to the map is your own business. But the map itself is worth looking at clearly before tonight ends. Consider the lithium problem one more time, not as a technical puzzle but as a piece of intellectual honesty. The standard model of Big Bang nucleosynthesis makes a precise prediction for the primordial lithium abundance, derivable from the same physics that correctly predicts the helium abundance to within a fraction of a percent. The observed abundance in the oldest stars is 2 to 3 times lower than that prediction, and that discrepancy has survived decades of work. It may reflect stellar physics. It may reflect observational error. It may reflect something missing from the theory. The reason this matters, at the end of a long night spent tracing the origins of the atoms in a human body, is that it is an honest report of where the map has an edge. The account given tonight is the best current account, the one supported by the most evidence, the one that has survived the most scrutiny, but it is not the final account. The lithium discrepancy is a reminder that there are still numbers that do not quite fit, still places where the theory and the observation sit slightly apart, still work to be done. There is a larger edge to the map too. and it is worth placing plainly because it changes the scale of everything tonight has described. The whole account, the hydrogen from the Big Bang, the carbon and oxygen and iron from stars, the gold from collisions, every element on Jennifer Johnson's coloured table concerns only ordinary matter, the kind made of atoms, the kind that builds stars and planets and bodies. And ordinary matter, as best we can measure, makes up only about 5% of the universe. The rest is unaccounted for in the deepest sense. Roughly a quarter of the universe appears to be dark matter, something that has mass, that holds galaxies together by its gravity, that the astronomer Fritz Zwicky first noticed was missing in the 1930s, and that Vera Rubin's rotation curves later confirmed must be there in great quantity, but which is made of none of the elements tonight has traced. It emits no light. It is not built from protons and neutrons. We do not know what it is. And the remaining 2/3 or so is dark energy, the name we give to whatever is driving the expansion of the universe to accelerate the effect first measured, as it happens, by watching exploding white dwarfs across cosmic distance, the same kind of explosion that made much of your iron. We do not know what that is either. So the entire story of where your atoms came from a century of work, a periodic table with a postmark on every element, is the story of 5% of the universe. The part that learned to assemble itself into stars and planets and the occasional observer. The other 95% surrounds it, shapes it, outweighs it many times over, and remains, for now, outside the account entirely. You are made of the part we understand. It is the smaller part. What is already established is more than enough to fill a night. The bulk of the map is not provisional. It is confirmed by direct observation, in several cases multiple times, through multiple independent lines of evidence. The uncertainties at the edges do not undermine the center. There is one more thing worth placing before tonight ends, and it is not a mystery, but a fact. The atoms in your body are not permanently yours. They cycle. The cells of your body are replaced at different rates, some within days, some over months, some over years, some never, and in that replacement process, atoms leave and arrive continuously. You breathe in oxygen and breathe out carbon dioxide, exchanging atoms with the atmosphere with every breath. You eat and drink and absorb atoms that were recently somewhere else in a plant, in an animal, in the soil, in the water. The carbon you exhaled a moment ago was, not long before, part of something you ate, which was part of a plant, which pulled it from the air, which had it from some other source before that, a chain of brief residencies with no permanent owner. The same carbon atom may have been in a tree, in an animal, in the ocean, in the air, many times over, long before it was in you, and will continue on its way long after. You are a place these atoms pass through, briefly, on a journey that began in a stellar core and will not end with you. Over a lifetime, most of the atoms in a human body will be replaced many times over. The atoms that are in you right now are not, for the most part, the atoms that were in you 10 years ago. The body is a pattern as much as it is a collection of matter, a temporary arrangement of atoms that passes through it rather than constituting it permanently. The atoms themselves belong to no body. They were in the interstellar medium for billions of years before they were in a living organism at all, and they will return to the earth, to the soil, to the water, to the air, when the body that holds them now is done. What those atoms do after that is a question for a different night. For now, they are here, 7 octillion of them, assembled into a body, lying in the dark. The night goes quiet now. The pace slows. There is an iron atom moving through your body. This is where tonight began, and it is where tonight ends. Not because the story has come full circle in a tidy sense, but because the iron atom is the right place to come back to. It is the element that cannot be made without an explosion. It is the element whose manufacture we watched directly, in 1987, in the light of a supernova 166,000 light-years away, tracing the decay of cobalt into iron for months after the blast. It is the element that arrives in your blood specifically because it was built at the limit of what fusion can do, and the star that built it, whether it collapsed or detonated, had no future beyond making it. The iron is moving slowly now. The heart is slower. The body is settling. Let the iron continue for a moment. It is in a red blood cell, which is in a capillary, which is in a body lying still. The cell is roughly 8 micrometers across, far too small to see. The iron atom inside the hemoglobin at the cell's core is far smaller than that. It is carrying an oxygen molecule picked up in the lungs a few seconds ago. In a few seconds more, it will release that oxygen to a tissue that needs it, and the cell will carry the iron back to the lungs to begin again. This is what the iron does. It has been doing this, or something like it, since it was incorporated into a living organism how many years ago. There is no way to say precisely. Before that, it was in the soil. Before that, in the ocean. Before that, in the cloud of gas and dust that collapsed to form the solar system 4.6 billion years ago. Before that, it was dispersed in the interstellar medium, drifting. And before that, it was ejected from an explosion, either a massive star that had burned through its entire fuel supply, reached the iron wall, and collapsed in less than a second, or a white dwarf that crossed a threshold and consumed itself entirely in a few seconds of runaway fusion. That explosion happened before the Earth was born. The iron has been traveling ever since, and for a fraction of a moment in the history of the universe, it is here, in a red blood cell, in a capillary, in a body that has spent tonight trying to understand where it came from. Here is the final fact, placed simply and left where it lands. The hydrogen in that body, the hydrogen in every water molecule in every cell, is nearly 14 billion years old. The universe itself is approximately 13.8 billion years old. The hydrogen was made in the first 3 minutes of that time. It has been hydrogen ever since. Nothing has changed it. No star has fused it. It arrived at the body it is in now after drifting through nearly the entire history of the universe, unchanged. And in the same body, a fraction of a millimeter away, is gold, 0.2 milligrams of it, distributed through the blood and the tissues, too small to detect without instruments. That gold was made in the collision of two neutron stars, the collapsed remnants of two massive stars that had lived and died long before the solar system formed. The collision produced gravitational waves. It produced a kilonova. It scattered a cloud of freshly synthesized heavy elements into the surrounding space, some of which eventually became part of the cloud that formed the solar system, then part of the Earth, then part of the organisms that evolved here, and then part of this body. We confirmed that this is where gold comes from in the year 2017. The hydrogen has been here since almost the beginning. The gold's origin was confirmed within living memory. Both are in the same body that is here right now, tonight, in the dark. The atoms do not know this. They are not aware of anything. They are hydrogen and gold and iron and carbon doing what atoms do, which is to participate in the chemistry of whatever arrangement they currently find themselves in. They do not carry the history consciously. The history is carried by the physics, by the specific isotopes, the specific abundances, the specific ratios that allow a scientist looking at the right instrument to trace an element back to its source. The body knows none of this, but the person in the body can. That is what tonight was for. Not to reach a conclusion about what it means, not to draw a lesson. The universe made this material across nearly 14 billion years and through some of its most extreme events, and at no point in that process was the material aimed at anything. It was not aimed at life. It was not aimed at this body. It arrived here through physics and chemistry and biology and time, and the fact that it arrived here and assembled into something capable of understanding where it came from is not something the universe planned. It is simply what happened. The hydrogen drifted for nearly 14 billion years. The carbon was forged in a stellar core. The iron was made in the death of one kind of star or the destruction of another. The boron was chipped from a heavier atom in the dark. The gold came from a collision, and here they all are, lying still in the dark. The night continues. The breathing slows. Somewhere in the body, an iron atom is moving through a capillary, carrying oxygen, turning back toward the lungs. Good night.